Good afternoon. Is everybody ready for the last two sessions, the home stretch of the conference? My name is John Johnson. This is Elena, and we're here to talk about the multiprocess QEMU project that we've been working on at Oracle for the last bit. We have a third member of the team named Jag Rahman, and he's unfortunately couldn't be with us in France here today. First thing we're going to do is I'm going to give a little bit of an overview of the architecture, and then Elena's going to go over this current status and how to use it and how you all can actually add to it. So, first question is, why would we want to do this? The answer is, everybody knows this, that QEMU is a hypervisor of choice in a lot of public cloud environments, and public clouds can host VMs from many, many customers. Most of them are just trying to get work done, but there's a few people who are up there, trying to be malevolent actors who want to snoop around either the host data or other tenants' VM data. And so public clouds need to plan for the worst case situations. They do that in many ways. Some of them use a different hypervisor. The downside of that is that QEMU provides a lot of features that are really desirable in a cloud environment, from live migration to emulating lots and lots of different I/O devices and having lots and lots of different I/O backends. Another option is just to minimize QEMU, reduce the attack surface by configuring as few devices and services as possible. And a lot of people just use VirtIO devices and the VirtIO user daemons to further reduce the attack surface. But the issue here is that reduces your ability to lift and shift on-prem workloads into the cloud, because some existing OS instances may not use VirtIO. They may rely on legacy interfaces. So the last one that a lot of cloud vendors are doing is just run each QEMU inside its own container. Then you can just place the VM's data in the container, use SE Linux or AppArmor policies to restrict the accesses of processes within the container. But the issue here is those policies apply to processes, and QEMU is a single process. So, monolithic QEMU, as I just said, it's a monolithic process that has a bunch of different functionality in it. Has a VM control plane. You give it a wide variety of command line options. You can monitor it over a QMP socket. You can do live migration, hot plug, storage snapshots, a lot of things. Second sort of big area of functionality is the KVM emulation, where for each CPU in your guest, it fires off a thread and then uses KVM to execute that thread under hardware acceleration. And this code just basically handles the guest exits and the interrupts. And the final one was probably going to be the focus of the rest of the presentation, is it does I/O emulation. It does software emulation of many, many, many different I/O devices. All these functionalities require QEMU to have a lot of host services. So any exploit that you do can actually allow a malevolent guest to gain all of and any of QEMU's access rights. So this is just a picture. It's worth 1,000 words of the sort of the current monolithic QEMU. You've got a big program. The guest is embedded within the address space of the process. You've got a bunch of different emulation modules in it, a control plane at the top, and the chipset emulation, which uses QEMU to execute the actual guest. All right, so why would we run QEMU in multiple processes? Well, as I said before, a lot of security policies are process-based. SE Linux is basically about rules that limit what processes to what files and device objects can access. Another one is SEComp. It can limit what processes to what system calls they can execute. So what we can do here by running QEMU in multiple processes is we can apply finer-grained privileges to each process. For example, if you've got a disk controller, you can only give it access to the disk images that belong to that guest. And even if you're using network storage, something like iSCSI, you can actually use SE Linux to keep that process from binding any port except the iSCSI port, or to accessing or connecting to any storage IPs except for the ones that are used as storage hosts. For SE SEComp, you can use we can have the device emulation processes limited from using fork or exec. So if you do actually gain access to those, you can't actually sort of escape out of the box and get a host shell and start rummaging around that way. So as I said, we're going to use, our first cut at this was actually to put device emulation in a separate process. That's a good place to start for a number of reasons. The most obvious one is that it's the largest surface area that a malevolent guest can attack. Most of the touch points of a guest to QEMU are via the MMIO operations that it does to the devices that it uses. The other one is actually just frankly ease of emulation. If you're, most of you should be familiar with the internals of QEMU. All these device emulations are actually implemented as objects. So we can actually use the object boundary, method boundaries to, as the separation point to proxy from the QEMU process to a remote execution process. And the last one is scalability. You can have the number of processes that you use to emulate your VM can scale up to the number of devices in the VM. Or if you want, you can actually sort of consolidate. You can have one process that does all of your storage that's limited only accessing storage nodes, or one process that does network that's only allowed to use say the tap interface to get outside of its world. And again, picture's worth 1,000 words. This is the situation we're trying to move toward, where you've got QEMU just has its control plane and the KVM management code in it, and the actual device emulations are all done with in separate processes that are connected over sockets to the main QEMU process. So a little bit about the QEMU object model. This is probably a review for almost everybody here, but the three main class models that we are playing with here is one is the machine class model, and that actually models the platform, the onboard. It assembles the onboard devices and does things like handling or create the objects that handle things like interrupts. The device class model, those are the actual, almost all the work is done. That's for each device, you actually have an instantiation of a device class for that device, that's where all the emulation code lives. And finally, there's bus class models, and model I/O buses, and they're basically used to enumerate the child devices of a specific I/O bus. So what happens when QEMU starts up? It obviously starts parsing its command lines. The machine argument fires up the machine model device to model the emulation objects and something like block dev to create a device backend. So the first thing that actually happens after it's parsed all the command lines is the device backends are initialized. And they're just placed on lists so they can be found by their associated devices later on. Then the machine object is initialized, and it sort of handcrafts the built-in devices, say an ID device, or for our purposes, the built-in PCI bus. And then finally, after the machine object is instantiated, the machine, all the list of device objects are all instantiated, and as they're instantiated, they look up their backend so they can actually do I/O to the host. So here it is, just in a picture. You've got the file backend to the right, which was created by a -blockdev argument. The minus machine created on the left the PCI 440FX machine class, which when it started up created a PCI bus. When it sees the minus device LSI SCSI, it attaches that emulation model underneath that PCI bus, and that emulation object, first thing it does is create a SCSI bus. And then finally, when you see minus device SCSI ID, that SCSI is hung off of the SCSI bus. So keep that picture in mind. We'll get back to it. So what do we actually do instead of just sort of look around what QEMU is doing? Our emulation process is actually running unmodified device and bus objects. This project does not scale if you actually have to go into the device object. Here's 3 things you need to change in order to make your device emulation run in a remote process. So we build it from the same QEMU source tree. We can have a little startup handshake to ensure that both QEMU and the remote process were from the same build. Same thing goes for the backends. They're built from the QEMU tree. They use the same command line arguments to be instantiated as you do in both QEMU and in a remote process. The thing we did new is we have a new machine class object. This thing, it replaces the CPU-specific one and platform-specific one that's in QEMU, but it performs a similar set of functions. It creates the initial machine, but instead of doing it from command lines, it does it from JSON descriptions that are sent from the QEMU to the, need to run a little faster. And the last thing it does is it handles interrupts and IMEI requests from the device models. The other thing we add is it needs to actually talk to QEMU, so we have a little proxy service to allow it to talk back to QEMU. That thing is the one that receives the configuration messages and instantiates all the device objects within the emulation process. And then actually at startup, it's the one that actually routes requests. So when the guest actually touches the device, it exits to QEMU. QEMU will forward, in a way we'll get to, the guest reads and writes to the emulation process, and this thing will route them to the correct device emulation object. Same thing for the other way. If the machine has a request that goes back to MMU, needs to go back to QEMU, this thing will route it back. So here it is as a picture. It looks exactly like the QEMU picture, except on the left we have a different machine object. Everything else you see is exactly the same code, same everything as you see inside a QEMU process. This is basically a mini QEMU process. So on the QEMU changes we needed something to invoke the remote processes. So we do that with a new -remote command line option. There are a couple flavors of it. One of them does, when you have an orchestrator like libvirt, it will probably want to fire off the remote processes, and it'll tell QEMU what a socket path that it's set up so that QEMU can talk to the remote process. If you don't have an orchestrator and QEMU is responsible for setting up the entire environment, there's a second option that you can give a command to, and then the QEMU itself will create the socket and execute the given command. There are no device backends for the devices that are being executed remotely. They're not needed at all within QEMU. The other big changes is what we call proxy objects that replace the device emulation objects. These are the things that actually forward the guest events such as MMIs to the emulation process. The way you specify those is just add a new RAD option to the -device. -device, everything else looks exactly the same. The RAD basically specifies which of the remote process managers he's going to forward his requests via. And they exist exactly like they do in the same place in the QEMU hierarchy, both bus and object hierarchy. So like an LSI is a subclass of a PCI device and is a child of a PCI bus. Other thing to note is that not all devices only need emulation, need proxy objects, only those that interact with a guest. So like the SCSI controller, since you do MMIO operations to the SCSI controller, needs one, but the actual SCSI device, which doesn't directly receive indications from the guest, does not. So as far as what the proxy objects looks like, again, we're reusing all sorts of QEMU code. All of the object, device, and PCI classes are exactly what are done within QEMU right now. We have a new one for PCI device proxy, and that's the one that's going to forward the guest config space accesses. For like bars, we need to be able to keep the PCI address to device mapping the same within QEMU and within the emulation process. So we forward bar programming from QEMU to the remote device. And then finally, there's a device-specific proxy that knows how big the MMIO space of a specific device is, and it forwards those operations. So what's left behind in QEMU is very, very simple. It's just the machine object that was created when you fired up QEMU. It created a PCI bus, and the proxy is hung underneath it. And then finally, just putting those two things together. On the left is QEMU with just the proxy in it, the proxy service going in between the two, and then the emulation code on the right. Again, the only thing that we've done are the things marked in red. Everything else is just QEMU, built from QEMU and executed like QEMU. And I'm going to hand it over to Elena, and she's going to talk a little bit about what current status is.
By now, you probably all want to see the code and play with this remote processes. We're not going to review the code now. Sorry, there is no time. But you still can go and play with the remote devices and QEMU multiprocess. And we don't have the patches upstream yet. We're working on that. But you can clone the version from the public Oracle GitHub. Go ahead and do that. Configure with the mpqemu key, build it, and you can run it. So probably people are concerned, like how many options, extra options I have to use to run it multiprocess? Well, not really many. And I have to repeat what JJ said. We have actually added one. Everything else is pretty much standard. We all know of them, and it's pretty much easy to run. It's very easy to run. Now, some people would probably think, well, okay, I have one process. Maybe I can run one device. Well, no, you can have multiple processes, multi-processes, and you can have multiple devices per process. You can actually try it with an LSI device. So this device was picked by us as a great use case scenario, and we decided to do the job on that. And you can see how you can run this device. Now, the functionality, which is right now implemented for the QEMU multiprocess, includes the QEMP monitor. So if you would like to use your standard QEMP commands with QEMU multiprocess, then you will just have to specify the socket for this remote process and use it as you usually use the QEMP commands, including the device hot plugs and others, though we actually do use reduced set of QEMP commands for remote process for now. Now, also we know that live migration is, for most people, is an important feature, so we added this too. So you could also play with that, and we did, and it worked. We also tried to apply as a concept as a Linux policy for our remote process. We did have an example of that, and it also worked. We also implemented libvirt support, which no one's seen yet. It's an older version, but we're probably going to work on it. Now, if you want to do more than just use multiprocess, what if you want to have your own device run in separate process? Then you don't need to do that much. Well, we hope. You just have to add your proxy. If it's not there yet, you have to specify the operations which are needed for the communication between the remote process and the proxy. You just have to modify the build system and add the QEMP commands you want to add. Now, in the future, what we want to do, this conference was great because we were able to talk to so many people, and we got great feedback, and we're hoping that people are going to take a look at the code and give some thoughts and maybe review that. There's a version 4 posted on the QEMU devel, and you're welcome to take a look at that. We would like to add more device types and improve performance and work on security more, and probably add libvirt support because it just makes sense. Should we talk about performance? Do we have time? We did run some preliminary performance tests, and we didn't notice significant performance degradation, but don't take them very seriously because there's more work to do on that subject. Any conclusion? Yep.
Good talk.
That's it from me.
That's all right. And we thank you for your time. If there's any questions, we can take them. Either everybody's asleep or that we did a great job.
So for devices where you have a proxy in the main QEMU and the real thing in the remote QEMU, how does unplug work? Do you need do you send the unplug command to the main QEMU, or do you send them to both?
For devices, we send it to the main QEMU. There's the remote processors do have a QMP socket, but those are mainly to manage the back ends of the.
Yes, that was my next question. So you need to know where the backend lives, so you send the QMP commands to the right QEMU, right?
Well, all device QMP-related QMP commands need to go to the main QEMU, because QEMU itself has a sort of a picture of of what the platform looks like. So if you're going to hot add or hot, and this actually does work. You can hot add or hot subtract devices from QEMU. And
Okay.
when it does, it actually send for like a hot add, it'll send the JSON string of the new device off to the process. And
what about the backends? The backends live only in the remote.
yeah.
And whom do I have to talk to if I want to interact with the backends?
Could you repeat that?
To which QEMU do I have to talk via QMP to interact with the backends that live only in the remote process?
Well, for a QMP command that applies to a backend, you have to apply that to the monitor socket of the remote process that has that backend in it.
Thank you.
Okay, if there are no questions, thank you.
All right, thank you. Thank you all.